Hello, everyone. Welcome back. Let us continue with the third talk in the afternoon session. In fact, the second talk. It is my pleasure to introduce our speaker for this talk, Dong-Young Lim. He is an assistant professor in the Department of Industrial Engineering at UNIST, and his research interests lie in machine learning algorithms, their convergence analysis and applications, especially in finance. In this talk, he will be speaking about Langevin-based algorithms for stochastic optimization and its applications. Dong-Young,
Okay, hi. Thank you for the introduction. And many thanks to the organizers for inviting me to this wonderful workshop. Okay, today I'm going to talk about Langevin-based algorithms for stochastic optimization and their applications in finance. Many modern problems in finance involving neural networks and machine learning and any AI techniques can be represented as stochastic optimizations. To solve such problems, researchers and practitioners use stochastic gradient descent or its variant like ADAM, which is basically developed in the field of computer science, and their performance was evaluated on the data set like image, language, or audio. Here, my question is that are they really working well for financial problem as well as in image problems? So in these talks, I would like to try to answer these questions by introducing new algorithm, so-called Diopla. Basically, this presentation is based on a trilogy of our recent 3 publications about Langevin-based algorithms for stochastic optimizations. This is outline of today's talk. Let me talk about background first. Okay, in the era of AI technologies, actually, AI technologies have been rapidly revolutionizing all areas of financial sectors. So, for example, some example includes some very classical quant problem like pricing, hedging, and calibration to more relatively modern problems like high-frequency trading. So let's look at some concrete example to see how AI technologies can be applied to financial problems. The first example is hedging for options, so which is very classical quant problem. So the goal is to determine hedging function delta from market data to minimize the variance of hedging performance. So traditionally, for example, Hall and White assumes to solve this problem assumes a certain analytically tractable function like quadratic function of Black-Scholes delta formula. And then they estimate coefficient of quadratic functions from market data. On the contrary, AI approaches directly approximate the target function delta market value minimum variance using neural networks, and then they estimate the optimal parameter of neural networks by minimizing the empirical loss function without restricting any structure of the target function. The next example is pricing American options. So in this problem, the goal is to calculate the price of American option from market data. Traditionally, well-known paper by Longstep and Schwartz assume that the early exercise boundary of American option is a piecewise linear function, which is quite too rigid for capturing real-world problems. However, AI approaches directly approximate the early exercise boundary using neural networks without any assumption on the early exercise boundary. And the last example is multi-period portfolio optimization, which is a very challenging, still very challenging problem in the literature. And the goal is to determine optimal allocation functions across multiple periods. So the standard approach to solving this kind of problem is to use dynamic programming. However, recently, some researchers in some papers, they try to approximate target function here, control how to allocate our wealth into each risk asset is our control function, and they directly approximate control function using neural networks. So through the examples I have introduced, have you noticed some common things they do? The thing is, they just approximate target function, which can be very complicated, using neural networks without any assumption, any restriction on the target function. Although I have to admit that there is some oversimplification in explaining the previous examples, but the key idea of AI approach in finance is to approximate target function using neural networks. This is very important because in traditionally, we try to approximate target function using some analytically tractable function like piecewise linear function or quadratic function, or any some tractable function obtained from elegant, beautiful mathematical model like Black-Scholes model. But we do not do that in AI approach. We just approximate target function using neural networks. That is the key. And this switch to neural networks offers very important advantages in scalability, and that is a data-driven approach. So we can avoid some model risk. And the use of neural networks is supported by the old and well-known argument, universal approximation theory. Okay, then now let's turn our attention to the Markov decision problem, which is our focus of this talk. So in MDP problems, we aim to maximize the expected objective function psi, and by optimally choosing our decision g0 to gk-1 at each time, and where each decision is within some admissible set U. And here, the state variable sk evolves according to transition function h that may depend on the current state and our control gk and some noise at k. So we are interested in these MDP problems. The reason I focus on MDP problems, many problems I introduced in the previous examples, like minimum variance hedging problems and multi-period optimization problems, can be represented as MDP problems. So, and usually, standard approach to solving MDP problems is to heavily rely on dynamic programming, which suffers from the curse of dimensionality, making it impractical in many practical settings. So, when in the era of AI, many researchers try to solve these challenging problems, high-dimensional problems, using AI approach. the idea is simple, just approximate target control function using neural networks. So here, target function G0 to Gk minus 1 will be approximated by neural networks, parameterized by theta. And then they just justify the use of deep neural networks with some universal approximation theorem, just stating that there exists some neural networks which is close to your target function. That is what they do. However, the important thing is this enough? Actually, no. The important thing is universal approximation theorem does not tell anything about how to find optimal parameter theta. They just state that there exists some neural networks which is very close to your target function, given any accuracy. So challenging part is to find and to train neural networks. So this is a real problem. However, so far, many in the literature, they just rely on popular optimizers such as stochastic gradient descent and ADAM, which is basically developed in computer science. And then they left some simple remarks like this. We know that gradient descent algorithm only guarantees converge to stationary point, which is lack of theoretical guarantees. But it is very excellent in practice, so we're going to use it. Another paper, it is well known that stochastic gradient descent may only converge to local minima, but it is very effective in practice, so we're going to use it without any theoretical justification. So a very famous financial mathematician, Sebastian Zaimonger, pointed out this problem and then mentioned the importance of optimization algorithm in the financial mathematics communications. So in this talk, in fact, carries adoption of stochastic optimization algorithm from the other domain can have some limitations. For example, as I said, they are only proven to converge to a stationary point, which is a theoretical limitation, and they require very strong assumption on gradient and data. So this assumption may not suitable for financial data stream. And many stochastic optimization problems appearing in finance have discontinuous stochastic gradient. For example, quantile estimation and CVA problem. And some researchers have found that there are they observed that ADAM can be unstable for financial tasks. So in this talk, I try to close this theoretical and empirical gap by proposing a new Langevin-based algorithms for deep learning solutions. So more specifically, in this talk, we designed stochastic optimization algorithm that aligns with the property of financial data. And then we provide full theoretical guarantees for the convergence. And we discuss some interesting connection between dynamic programming and transfer learning. And then lastly, we demonstrate its good empirical performance in multi-period portfolio optimization problems. Okay. So recall that in these talks, I'm gonna focus on the MDP problems, which is maximization problems of expected value of objective function. And by optimally choosing our control function G0 to Gk minus 1 sequentially, and state variable are changing with respect to time according to some transition function. And as is shown in example 3, multi-period portfolio optimization problem can be viewed as MDP problems. So more specifically, we want to maximize the utility function of I put minus and then change in minimum. So I try to minimize minus utility function of terminal wells by optimally choosing our wells allocations. So here, GK control function is the investment control, how much we're gonna put our money in each risk asset. And one of state variable, the wealth of the portfolio at time k, denoted by WK, will be evolving like this. Then, depending on our assumption on return process could be anything you want, but for example, Black-Scholes or autoregressive models, we can specify our NDP problems like this. Then, as I said, we want to take AI approaches. And the main idea, as I said, main idea is to approximate our target function. Here, our target function is control functions, set of control functions, using neural networks. So we would like to solve NDP problems by restricting GK, which belongs to neural networks. So we restrict our control function to be neural networks and then solve this kind of optimization problems. So here, I would like to refer for this approximation to refer to this paper for verification of this approximation. I don't want to dive into in this direction in detail. So, but the important observation here, our sequential problem, original sequential decision problem, MDP problem, is now transformed into an unconstrained optimization problem. So our MDP problem has now changed to some unconstrained optimization problem. And this is the specific architecture of deep neural networks for this problem, but let me skip in detail. So our problem is now this kind of unconstrained optimization problem. So in our multi-period portfolio optimization problem, our objective function will be minus terminal utility function obtained from neural networks. And let denote H by gradient of objective function U and define stochastic gradient of U denoted by capital H as an unbiased estimator of true gradient H. And we assume that stochastic gradient capital H has the following form, G plus F, where G is measurable function and F is continuous. Here, G can have some discontinuous because, as I said, many financial applications have consider problems like involving stochastic gradient to be discontinuous due to CBA or neural network with LELU activation function. And this is some technical assumption for our problems. So the first assumption is about initial parameter and data process. And second assumption is about gradient G. G can have discontinuous, but in average, it satisfy local continuity with some growth condition. And F gradient, another part of gradient F satisfies some local Lipschitz continuity with some growth condition. And fourth assumption is local convexity at infinity. And the important is, what's important here is by assumptions 1, 2, 3, 4, we can derive some dissipative condition, which is contractive conditions. So the intuition of this condition implies that all stationary points are contained within certain ball with radius of scalar of B over A. So when you put the stationary point where h theta will be 0, then you can easily see that kind of property. And the important thing is that in many applications, including quantile estimation, CIVA minimization, and regularized optimization problems involving ReLU networks, they satisfy assumption 1, 2, 4. And then to solve these optimization problems, we take Langevin-based algorithm. We're gonna study Langevin-based algorithm. So let me briefly talk about Langevin diffusion first. Langevin diffusion is given by this kind of SDE, and here H is the gradient of our objective function. Then if we take this, if we take our drift in the SD as the gradient of our objective function, we have very nice theoretical fact. The solution of Langevin diffusion converges to its invariant measure, denoted by pi beta. And more important here is this invariant measure is indeed Gibbs measure, which has form of like this, exponential to the minus beta times u of g. Let me recall that u is our objective function for our optimization problem. Why this is important to solving optimization problems? Let's say that we have this kind of objective function, which is truly non-convex, but we can tell that this point will be global minima. Then when I plot the invariant measure with beta being 1, its invariant measure will like this. And when I set beta to be 10, then the invariant measure will be like this. And when I set beta to be very large enough, then invariant measure will concentrate on global minimizer. So this implies that our optimization problem can be viewed as sampling problems of invariant measure of Langevin diffusion. So now our task is to sample invariant measure of Langevin diffusion. So the standard approach is to discretize Langevin diffusion using Euler-Maruyama scheme. So, but in practice, it is not viable true gradient in practice. So we usually use stochastic gradient, which is unbiased estimator of true gradient H. Then when we replace true gradient with stochastic gradient and then apply Euler-Maruyama scheme, then we're gonna get this kind of stochastic gradient Langevin dynamics. However, this kind of naive discretization has very limitations in high-dimensional optimization problems because SGLD has very slow mixing time. So we have to modify this SGLD to improve the performance of our optimization algorithms. So here we propose so-called Theopula based on Euler-Kirchhoff approximation, not Euler approximations. So the difference thing is here H was a standard stochastic gradient, which is independent of step size lambda. But here, by applying Euler-Kirchhoff approximation, which allows us to depend on step size lambda. This flexibility allows us to combine very good feature of stochastic analysis. First one is taming functions. So taming function is well-established techniques in stochastic analysis to control superlinearly growing gradient. So we can combine this kind of taming function for our algorithm, and we devise boosting function to control some vanishing gradient problems. The proposed algorithm, Theopula, has two features. One is taming function, and second one is boosting function. So taming function is basically controls the superlinearly growing gradient, and boosting function try to prevent some vanishing gradient issues by boosting the step size. And as you can see, updated rule has some scaled noise from discretization of Langevin diffusions. So let me briefly explain why this kind of structure is really working well for real-world problems. So our problem, let's say our learning problem, is very complicated and high-dimensional. So it can be this kind of, it has this kind of landscape, very complex. So it can have a very flat region, and simultaneously it can have very steep and narrow gradient. If we use a single learning rate, like in SGLD, it cannot move on in flat region, or it can explode in this kind of steep and narrow regions. But our proposed algorithm has adaptively controlled this kind of pathologies. For example, let's look at the region, first region, where loss function is steep and narrow. In this region, our stochastic gradient is very big. So our step size should be sufficiently small to safely go on to the minima. Here, when H is very large, it will control the magnitude of stochastic gradient. This is how a taming function works. At the same time, H is very large, then boosting function will be close to 1. So boosting function will not work when H is very large. On the other hand, when we look at the region 2 here, where loss function is very flat, so there is very small vanishing gradient issues. In this region, we have to boost our step size. So we can do, so it is ideal for our optimizers to take large step size in second region. It is possible for Theopula because when H is very small, taming function will be 1, so which is nothing. And boosting function will be here, this is very small. So this amount of boosting effect can be appear. So we can boost our step size when h is very small. So our proposed algorithm can handle both vanishing gradient issues and exploding gradient issue in a very harmonious way. And then we studied some convergence analysis. When we set our approximate solution after n iterations, and then we measure the distance between our approximate solution and invariant measure in Wasserstein 1 distance, and we have obtained some best known rate, convergence rate in Wasserstein distance 2 as well, and we have derived from that we could derive optimization error as well. And then I would like to introduce some very interesting link between transfer learning and dynamic programming. So this is very interesting observation. Let's say that we have solved neural network problems for multi-period portfolio optimization problem with terminal time t. And then after some time, we want to calculate the same problem, but different terminal time t plus 1. Then there are two options. We retrain neural network from scratch, which will be very inefficient and time-consuming. But here, we already have trained neural networks for terminal time t. So can we reuse these retrained, these trained neural networks we already have? This is our question. So we have a linked dynamic programming principle and transfer learning in this kind of questions, and then we could find very interesting result. So even if we have different, when we have different problem with different terminal time, we can reuse a trained model which we already have. So when we calculate multi-period portfolio optimization problem with terminal time k plus 1 using trained neural networks with terminal time k, using only one single neural network. Otherwise, if we didn't take this approach, we have to use k plus 1 subnetworks, which we have to train k plus 1 subnetwork, which will be very time-consuming and inefficient. So this is a very simple message for transfer learning and dynamic programming principle. And then let me briefly introduce some numerical result with our algorithm. So we have conducted some extensive numerical experiments for multi-period portfolio optimization problems. Firstly, we assume that our return process is following Black-Scholes model. So which is very simple because Black-Scholes model assumes independent return process. So there will be only one dimension 1 state MDP problems. This is we have simulated with very different hyperparameter sets like this. Here, P is the number of dimension, number of risk assets. So when P is 5, there are 5 risk assets we can choose. So we solve multi-period portfolio optimization problems using different algorithms such as SGLD, which is a basic form of Langevin-based algorithm, and TUSRA, which is some advanced algorithm, and then variants of SGD like ADAM and AMS CRUD. As you can see, our algorithm, Ethiopia, achieves similar or better scores in across many different number of dimensions, like this. Actually, this is Black-Scholes model case is relatively easy. However, when we consider some return process will be dependent on the previous past history, like a autoregressive model, then this problem becomes extremely difficult. So when we take our return process to be autoregressive models, then there is no analytical or numerical method to solving high-dimensional NDP problems. So here we have solved these problems using different optimization algorithms. There is no benchmark, so all we can compare is just directly compare the test score obtained by each optimizers, and then lower is better. So as you can see, each optimizer have different test scores, which means depending on the choice of optimizers, your performance of portfolio optimization can be very different. This is very important. So as you can see, Ethiopia can achieve the lowest test score, which is the best result compared to other competitor algorithms. So let me give you my last takeaway message. Based on our experiments, we have observed the following. First of all, I have to say that ADAM is excellent, excellent optimizer when you need reasonably accurate solutions very quickly. However, when you, I'm not sure whether you have experience in implementing ADAM or not. When you put hyperparameter tuning, when you put your time and effort in hyperparameter tuning, it is hard to achieve further improvement with ADAM. Furthermore, as I said, ADAM has no theoretical guarantees for convergence. On the other hand, Langevin-based algorithm, especially our proposed algorithm, can outperform ADAM if careful hyperparameter tuning is given. In addition, our algorithm is supported by a theoretical result. So when you need some theoretical guarantees on convergence are critical in your task, or you are dealing with some very complex deep learning architectures, we recommend you to consider Langevin-based algorithms over ADAM. This is main key message of this presentation, and thank you very much.
So Theopula is different from TUSLA because of this boosting epsilon the case. So what's the philosophy of this epsilon? How do you choose it?
Actually, that depends on the problem. Yeah, So each problem has different landscape, loss landscape, different curvature and different gradient. So we have to find optimal hyperparameter epsilon, which means this is we need to pay attention for some hyperparameter tuning. Yeah.
Okay.
But there is one more difference between Tusla and Diopla. Tusla has a global taming function, which kills the gradient in very high dimension. But in Diopla, we use element-wise taming functions.
Thank you.
There are some problems in which you don't have the true minimum of the optimization problem, right? Like the American options case, because you have lower bounds, but you don't know in principle the exact minimum. In that case, how you justify your method for that?
Oh, sorry, say down.
Yeah, I mean, the convergence of your optimization method, is that guarantee for any type of problem?
If assumptions are satisfied.
Mm-hmm. But in case of portfolio optimization, for instance, there are cases in which the objective function and the constraints of the optimization problem will not give you a minimum. It's not known the minimum, because it's a NP-hard problem. So in that case, how your method would apply?
Maybe I could answer you.
I give you an example. You may have a mixed integer problem.
Yeah, like this. In this problem, AER models, multi-period portfolio optimization on the AER model, there is no analytical or numerical method to solve this problem. So we don't know what is the global solution.
Exactly.
So all we can do is just compare the test scores obtained by different optimizers.
And you take the minimum.
Yeah. And then our solution, our method finds minimum point compared to other solutions. Then it is good. That is all we can do. Yeah, actually.
All right. Yeah. Thank you.
Do we have any other questions?
Thanks for the talk. I'm just wondering, do you have any guidance on how to choose the noise, like the magnitude?
That is a very difficult question, because as far as I know, there are many variants of Langevin-based algorithms, and relatively, compared to stochastic approximations such as Adams, it is very hard to tune hyperparameters. But my guidance is basically SGLD and Diopla will behave like SGD rather than Adam. So you have to start with large step size rather than very small step size like Adam. Yeah, that is all I can do. Advice. And beta should be large enough. Yeah, there is some annealing strategy as well, but that is another direction. When you use some fixed beta, high inverse temperature, you have to choose very large beta. Yeah.
And maybe the large batch size to start with?
Yeah, large batch size, or as far as based on my observations, batch, they do work well regardless of size of batch size. Yeah.
Thanks.
Thank you very much.
If there are more questions, we can discuss after the session. Let us thank the speaker again for the.